gradients. What's a gradient? So let's say you have a function of two variables, or you can also have three variables. Gradients are defined for any multivariable function. A gradient of a two-variable function is the following. It's simply a vector made up of its partial derivatives. That's what gradients are. And then if you had a three-variable function, it will be round f, round x, round f, round y, round f, round z. Just come up with the vector. So gradient takes any multivariable function and creates a vector out of it. That's what a gradient is. Let's think about an example, e.g. suppose your fxyz is equal to xy plus 4z cubed. Something like this. In this case, what's the gradient of f? Okay, first, you have to take this and differentiate by x. What do you get if you differentiate by x?
Y.
Y, right? This is considered as constant if you're doing partial differentiation. Partial derivatives consider all the other variables as constants. So when you're differentiating by x, y is considered as a constant, z is considered as a constant. So this is actually just entirely constant, which goes to 0 if you differentiate. If you differentiate x times a constant by x, you just get that constant, right? Because x differentiates to 1. Right? What do you get if you differentiate by y? X. Now, what do you get if you differentiate by z? So in that case, both x and y are considered as constants, so that goes away when you differentiate by z, and when you differentiate this by z, 3 comes down, multiplied to 4, and you get z squared. So that's the gradient. Easy, right? Okay, well, it's easy to calculate, but you wouldn't know the meaning of a gradient unless we try to relate this with the directional derivative. Okay? So here's what we want to do. First, think about the formula. Recall the formula that if you had a vector u, which was a unit vector a comma b, the directional derivative of f with respect to u was you first differentiate f by x, multiply by a, plus differentiate f by y, and multiply by b. Okay. That was the formula. Another way I wrote this was when a was cosine theta and b was sine theta. Sometimes it's written as this times cosine theta, this times sine theta. That's another formula. But it's the same thing. Just think about a itself as the cosine of some angle, b as sine of some angle. All right, but anyways, this is the formula for the directional derivative. Now, do you see the gradient embedded in on this right side? Right? This and that, right? So we have this vector appearing here, and this vector also appearing here. Now, what kind of operation between these two vectors would you do to create exactly this? The dot product, exactly. So you have directional derivative of f represented as gradient of f dotted with u. Now there's another formula, another symbol for gradient. Sometimes writing GR80 all the time is time consuming, so people simply just write down this symbol, nabla. This looks simple. Okay, so another symbol for gradient is nabla of f.
Do you have to make the f a vector? Like you have to put like a...
Oh, yeah, you're right. I think in the textbooks they just use boldface for vectors, so they don't really care, but since I can't write down boldface here, I should really write down this vector notation on top, just to make sure that you know that it's a vector. But, you know, habits die hard, so since I often just write down nabla f, I'm going to do that, okay? But just, okay, by the way, this symbol here is called nabla, nabla. You should think of that as a vector object. So if you multiply that to a function, it becomes a vector. Gradient of a function dotted with u. So we have a really simple formula now, which is easy to remember. And that's the one that you should remember. Okay. So now you can forget about this formula or the version with cosine and sine. The only thing that you have to remember is whenever you're being asked to find the directional derivative of a function in the direction of u, you're supposed to simply take that vector, take that function, find the gradient, and dot it with the unit vector. That's what you have to do. Okay, now, because of this property, you can start making sense out of what gradients really do. So let's try to relate, first let's try to relate the directional derivatives with level curves. And after that, I'll try to relate it to the gradients. Okay. So here's let's say here's a function with some level curves. Let's just say it's like the function is shaped like a mountain top. So that's the level curve. If you forgot what level curve was, it's like, you know, a function of two variables x and y is like a surface in 3D. Right? At each point you have the height z. Right? And one way to represent that surface is to draw a terrain map. What do you call it? There's another name for it. Huh? Topographic map. Thank you, guys. So you would want to draw the topographic map and say, oh, here's level 0, here's level 1, here's level 2, here's level 3, and then you can kind of picture this surface almost, right? Just looking at this, you know that, oh, it's some kind of surface that's shaped like a mountain. Right? Now, let's call this point A, B, and let's say you have a vector first, vector u1 here, and then let's say here's another vector, let's call another vector, it's like this, let's call this u2. And then let's call a third vector, which is like that, U2, U3. I made them look like different sizes, but I meant they're all unit vectors. Okay. Because when you talk about directional derivatives, you have to use unit vectors. Okay. All right. So here's a question. Is the directional derivative of f with respect to u1 positive or negative? Or 0?
Positive.
Why? Why do you think so?
Because it's going up in a sense.
So if you're going in this direction, the value of f increases, right? And in calculus 1, you learned that if the function is increasing, the derivative is positive. Okay? So this is... Now how about directional derivative with respect to u3? Oh, I forgot to say of a comma b. What about this value?
Negative.
It's negative because, see, this is the mountain, and if you go this way, you're going downhill, right? So it's negative. Then what about u2? Now, by u2, I meant this tangential direction. If you go along this tangential direction, what would happen to the derivative? The directional derivative will be 0. Because if you move along this curve, is the value of f changing? No, because this is the level curve with z equal to 1. So if you move along this curve, the value of f does not change, and therefore, if you look at the rate of change as you're going tangential direction, there is no change of f. So that's what happens. Okay? Any questions so far? Okay. So I guess you agree with all of these analysis here. Now here's another way to think about all this phenomena. We have this formula here, right? That the directional derivative is same as gradient of f dotted with u. Now, so let's start with this. You have gradient of f dotted with u2 equal to 0. Right? That's what this means. This is same as this. Right? This dot product is same as the directional derivative. And we have these two vectors dotted, and 0. Now what does this mean for this gradient and this vector u2?
Perpendicular.
Perpendicular. Why? Because if you have two vectors dot product to give you 0, that means those two vectors are perpendicular, right? So now you see that either the gradient of f is pointing to that direction or that direction. It's either one of those two. Okay? Now let's figure out which one it is by looking at this one. Okay, so let's look at this one. This one says your gradient of f dotted with u1 is positive. Now in this case, what's the angle between the two vectors? Is the angle between the two vectors acute or obtuse? If the dot product is positive, the angle between the two vectors is less than 90 degrees or more than 90 degrees? Less than 90 degrees. So these two vectors have angle less than 90 degrees. Now here's u1. Which one is gradient of f then? Going this direction or that direction? Going uphill or downhill? It's the uphill one because this is that has the angle less than 90 degrees. if this was so, then the angle will be obtuse. There's no way this could be possible, right? So we know that the gradient is perpendicular to the level curves pointing to the increasing direction. Okay, so we can have some good understanding of the meaning of the gradient by using this relationship that the directional derivative is same as gradient of f dotted with u. The first fact is that the gradient of f is perpendicular to level curves. Now, we could have defined directional derivatives in three-dimensional space in the same manner. And if you do, you'll see that this is still true in three-dimensional space. And that's even better. Imagine how complicated this formula would be if you didn't have the gradients in 3D. Okay? But even in 3D, this is true. And in 3D, instead of level curves, you have something called level surfaces, because if you have a function of 3 variables, and if you say this is equal to constant, well, this is an equation in 3-dimensional space. So if you have a 3-dimensional space and you have an equation, one equation gives you one surface. Okay? So instead of level curves, you have level surfaces in 3D. And in there, because the same relationship holds, you can also say in 3D, level surfaces. Okay, so that's the first fact, that gradient is perpendicular to level curves or level surfaces. And then number 2, gradient of f points to the fastest increasing direction. Now, why is that? Well, look at the following. You have this formula, but you can write down this directional derivative using the formula for dot product. The formula for the dot product says it's the norm of the first times the norm of the second times the cosine of the angle between, right? What's this value? U. U hat norm. What's that? What? Somebody said that. 1, because it's a unit vector, right? So you end up with gradient of f dotted with u equal to gradient of f norm times cosine of theta. Now, what's the maximum value of cosine theta? Can cosine of some angle be equal to 2? 3? What's the maximum value this can have? 1. Right? Now, when does this attain 1? For what angle?
0.
0. Okay. So that means when your direction vector u is aligned with the same direction of gradient of f, the directional derivative is maximized. And the maximum value is this one because it's this times 1. Right? So that gives us two things. The direction in the direction of the gradient gives you the maximum. That's why gradient of f points to the fastest increasing direction. That's the first argument. And then third, the maximum value the directional derivative can have is the norm of the gradient. So, norm of the gradient is the maximum possible value of the directional derivative. That means we can define gradients in a purely geometric way, here's how you define in purely geometric way. At a point, if you want to know the gradient, what do you do first? It has to be perpendicular to the level curves, and that's the direction where the function will be increasing the fastest, right? And then, so I have the direction, and to define a vector, you need the direction and the magnitude, right? What's the magnitude? Well, the magnitude will be the directional derivative of this function with respect to the unit vector in the same direction of the gradient. Okay. That's how you define a gradient geometrically without using the formula. Of course, we would use the formula usually to calculate because that's easier to calculate, but the meaning of the gradient is exactly this. Now, this has some useful consequences. So for example, if you're here and you want to reach the top of the mountain in the shortest distance, what do? You have to follow a path where it's always tangential to the gradient. So if you're at the bottom of the mountain, if you want to find the route to the top in the quickest way, you want to always move in the direction of the gradient. If you do that, you reach the top the fastest. Now, in physics, what happens is things fall down with the forces acting in the direction of the gradient because it tries to move to the gradient, right? It doesn't lie in the trajectory where the tangent vector is the gradient. That's not true, but the forces acting on this thing that's rolling down always points to the gradient, okay? And that's a very good way to determine the trajectory of a moving particle when it's in a potential field. Okay? So this applies to the case when you have a three-dimensional potential field like this, when your potential is really the gravitational potential energy. Or you could also use this in a context of electric fields. Okay? If you have electric fields due to some electric potential, then in that case, this particle that's charged will move using this gradient technique. Okay? So it's very useful.